Hi, Dr. Borrelli. Can you hear me? I cannot hear you though.
Can you hear me?
Yeah, I can hear you now.
Good. Hi, what is your name?
Nishant?
Hi, Nishan. Oh, you're the guy writing to me. Thank you, Nishan, for inviting me here.
Yeah, thank you so much for joining us today.
No problem.
Yeah.
Nishan,
Yeah.
visually, who's the audience here?
So, the all of the meeting is gonna be streamed live onto YouTube, and the audiences are on YouTube. So, if there's gonna be any questions at any point, I will relay all of the questions to you. And
So this is not Cornell students.
it is Cornell students, so it's like we have it on live stream and then we record it for people to view it later. And like usually Cornell students join it and others go and view the seminars at a later point. And my advisor, Dr. Malikopoulos, sends his warmest regards, and he'll also be joining the meeting via the stream.
No problem. We usually you start on time or you start a few minutes late.
We can start on time.
Okay. Do you take
Meanwhile,
question? Do you take question on the this is gonna be, I think, 45 minutes. You take question during the talk or not?
it's totally up to the speaker. So like it's up to you to decide if you want questions
Okay.
at the end. Uh, yeah, yeah. And meanwhile, if you would like to test your shields screen sharing,
Sure.
sometimes.
Uh,
Yeah, and please feel free to take a bit longer if you'd like to. Like 45 minutes is just the norm, and we could always go a bit over that. Yeah, I
do you see
can
my
see it.
screen?
Yeah, yeah.
Can we, one thing, if I wanna see show the audio, advanced option.
Yeah.
Let me get the video. Uh, do you hear the audio or not?
Oh no, I'm
Okay.
unable to hear that.
Okay. So let me stop share. Share again. Advanced sharing option. Uh, yeah, the share sound is blind as blank. I don't know why.
Um, check.
Can you see? I cannot share sound. See why I'm Googling what's going on.
So I can give you the host permission. Then could you check again if you're able to go into the sound sharing option?
Just share. Do I want me to reconnect?
No, no, I can just make you the host just to check.
Okay, just
Yeah,
make me the host.
yeah.
Okay, share. No, the option is not there. It's blank. Do you see? Can you try to share the screen? Try to share, and then on the right hand side, go on share, and then go on layout and option. You see the share sound is grayed out. Is it grayed out for you?
Yeah, I'm trying to share my screen now.
No, before you share.
Oh,
So stop sharing, share, and then on the right hand side, it's written at bottom right, it's written layout and option. You see, and it's share sound. Is it grayed out for you?
I, I'm not able to get to that option.
When you see the share blue share screen, uh, the blue button on the right hand side is written layout and options.
Okay, check. I don't get any options when I try to share
Oh,
the screen.
okay,
Yeah,
even
I'm
worse.
sorry. Yeah,
Just yeah,
yeah.
it's okay. I think we can. I guess we have to do without. It's a pity. I don't see how we can do this. Uh, yeah. Let me do one more check on Zoom.
Yeah. I can go and check on the internet.
Share sound option. Not available. It's grayed out. Let me see what's going on. Do you wanna try share multiple screens simultaneously? Can you
Yes, let me try that.
allow it to share multiple screen? Enable sharing multiple screen. Let's see if that works.
Yeah, yeah. When I try it, I'm not able to share multiple screens at the same time.
I see. Okay, you have some settings have been set up
Yeah.
for us. Okay, let's get started. Uh,
Okay. I'll just start with an intro and then
yeah,
you
just keep it
take over.
short. Don't worry.
Yeah.
I will. Let me start before you learn from the beginning. 1 second.
Yeah. Yeah. And could you
Uh,
please give me the co-host or like host permission just to?
okay.
Yeah. Yeah.
Right click. Advanced. Make host.
Yes.
Yes.
Yeah. Thank you.
Okay.
Yeah. Yeah. I can see your screen now.
Okay.
We can
Good.
start. Okay. Just a second. Hi everyone, welcome back to the DDLC seminar series organized by the IDS Lab at Cornell University. This is Nishant, and today's talk is going to be about automatic control in the era of artificial intelligence. And it's a pleasure to introduce today's speaker, Professor Francesco Borrelli. He is the Fanwip Professor at the Department of Mechanical Engineering, UCB. Dr. Borrelli received his laureate degree from the University of Naples, Italy, and his PhD from the Automatic Control Lab at ETH Zurich. And he's currently a professor at the Mechanical Engineering, UCB. And his research interest is in the field of predictive control, uh, and more specifically, model predictive control, learning, and their application to robotics, transportation, and energy control systems. And he has contributed to over 200 publications and modeled a book on predictive control. And he has received several awards, an NSF Career Award in 2009, an IEEE Control Systems Technology Award in 2012, and he was elected IEEE Fellow in 2016. And in 2017, he was awarded the Industrial Achievement Award by the IFAC Council. And he's also a founder of uh, two big companies, Pridebox and Whitesense, and he's also a co-director of the Hyundai Center of Excellence in Integrated Vehicle Safety Systems and Control at UC Berkeley. And without further ado, I'd like Dr. Berelli take over. Thank you.
Thank you, Nisha, for inviting me. It looks like we are streamed, so I won't be able to see participants. Is that correct, Nishan? Yeah, okay. So this is usually a seminar that doesn't come well when it's. I hear some background noise. Is all good?
Yep,
Okay, good. Okay. Seminar doesn't come well when it's streamed online. This is, I like to interact with people and get feedback on this seminar. I've given this a few universities, and what I've tried to do here with this pretentious title is to tell you a bit about my experience with automatic control and how that's in current era of artificial intelligence. So I'll divide the talk into 4 parts: an introduction, some background on basic control design, the role of AI and control in control applications, and the role of AI in new control theory, and then I'll conclude. I also, let me make sure I don't have a pointer here, but you probably should be able to see my mouse. So let me start with the following observation. As I was putting this talk together and I was learning, I was studying relevant material, I realized that this statement from Derek Thompson from the Atlantic was really relevant. It was relevant before, as he states, we're learning more and more about the world every year. And the more we learn about the subject, the harder it gets to push the boundaries of knowledge outwards. And so this is true in our field. So for instance, if you look at an interesting interview that Yuri Nesterov gave a few years ago at ETH about this field in optimization, saying that this field is very fragmented. There's just way too much. There are lots of optimization methods and all of them work. Okay, and so we don't in the optimization field, we don't say forget about this method, there's a better method. So this is even more pronounced when you think about AI and control, right? Because it is a large field. There is lots of opinions, and my one of my observations today, the first observation is that this field is becoming more specialized, divided than ever. And so what you will hear today in this seminar is a story that is biased towards my own experience with control design and artificial intelligence. So what are my own experience? I've been for the past 25 years, almost 30 at this point, I've been working on automated vehicles, on vehicles powertrain control, of building heating, ventilation, air conditioning, and solar power plants. So I'm going to use the experience that I've in my career in designing control system for this class of applications for tell you what is my view on control application in the era of artificial intelligence and what control theory means nowadays and the role of control theory that plays for designing safe control systems. So I like to define, and I've defined things, and I've used this AI, this term is used, and I've already mentioned a few times. So in this talk, AI for control really means any technique which is used to data to design or update an output feedback control policy. You start from measurements, you want to compute control inputs, and if you use any data, whether it comes from simulation, real-time experiments, webscape data of any format, whether there are images, time series, or videos, then it might also be referred to an AI control method. So on what we have in our field, then on one hand, you have an advertised revolution. So you can, for control design, when AI is used for control design. So you have amazing videos of robots jumping, walking, driving, flying. Then the message is that you get impressive performance with apparently minimal design effort. And so the this is today, this is everywhere in the news, and this is what the general public feels about AI for control design. Well, in reality, is that the field, from a scientific point of view, is divided. And I put two extreme examples. You maybe over exaggerated. On the left hand side, a colleague from MIT whose background is an early background was on model predictive control and using methods for optimization, where talking about imitation learning. Okay, says that his experience had given unbelievable robustness if images were within distribution, its behavior was within distribution. And yet was forced to reflect on his core belief on the value of this type of control methodology, imitation learning. On the other hand, totally opposite background from Yann Khan, head of AI at Meta, where is suggesting that you should abandon imitation learning, reinforcement learning, and you should favor model predictive control. Okay, so again, these are exaggeration of the two extreme, but it shows it reflects upon some of the sentiment of the extreme sentiment of the community here of the role of AI for control design. So that I'm going to do next, for people that are not familiar, usually I give this talk to a general audience and not familiar about these words, MPC, reinforcement learning, and imitation learning. And I'll give you a 10 minutes background on this control design technology. I'll start from a classical model predictive control, and we're going to use this diagram to tell you in gray what you need at design stage, meaning while you're designing a controller, and the blue box what happens in real time when you take sensor measurements and you compute control input you in at every sample time t. So in classical model predictive control, you need offline to pick a policy class. Usually this policy class is parameterized of phi, is piecewise constants. So in this case, your parameter phi are actually the input at constant samples. Then you have to pick a model to forecast your behavior. You have to pick a cost Q to mean that using your performance index and your constraints. You also need a target stat and a terminal cost, because usually you're short-sighted, and if you don't design them properly, a model predictive control will not work well. And usually you need to teach control upon a function, variable function, invariant set to properly design these elements. In real time, once you have chosen these elements, then the input, the controller needs to a numerical optimization solver to find the best parameter phi of your policy or your parameterized policy. And in general, because the model, it's a state model, you will need an observer design to go from the output Y to the estimated states to fit to your forecast model. So once you have the parameters that come from the numerical optimization, then the evaluation of the policy is simple. So what happens in now learning model predictive control? We've been working on learning model predictive control for 15 years now. It's what's happening as you scroll through this set of slides, the number of design parameters, the number of design elements becomes smaller and smaller. So I got rid of terminal cost and terminal set. You still need a policy class, a cost, and a modeling constraint. And you add this learning element here with this green, in this green box that takes input output pairs and learns a parameterized representation of the terminal cost and terminal set, and possibly also learns a parameter representation of your forecast model. So these parameters data now in real times are fed to your optimization engine. You still need a numerical optimization for compute the best set of parameters phi that enters your policy. You still need an observer design, but once you solve this optimization problem, then again, it's simple to evaluate your in real time your policy as a function of the measured output y. Let's now move to reinforcement learning. The community sometimes this is also they know this approximate dynamic programming. What happens here? I get rid again on one element. So as I mentioned before, I'm scrolling. I'll go back to my MPC, focus on this gray box. Look at how many elements you have. With learning MPC, you have fewer elements. With RL, you have even fewer because now a few things happen. You get rid of your constraints, you embed them in your cost function, usually as an indicator function. Your policy parameter, your policy class is usually a neural network. So phi are the weights of the neural network. The model is often a simulator, and the cost in general is over one-step prediction. So the learning now, usually it's offline and really refers to learning the policy parameters, using input-output pairs from experiments or from simulations, usually using some form of policy of various iteration. So once you have the best parameters phi star of your policy, in this case, in general, the weights of your neural network, the real-time implementation is simple input-output evaluation of your policy. So this is much simpler to implement than the technique that you've seen before. Finally, let's go to imitation learning. If you see in the gray box, it's pretty much, it's very little left. There is a very smart selection of a policy class, which is usually often again a neural network, and a smart generation of a large data set. This large data set of input-output pairs is then generate offline. It's used offline to learn the policy parameter by simple regressing the expert behavior. You're looking for the parameter that best explain your observed input, and usually you do that with some kind of numerical optimization, stochastic graded descent. But most importantly, if you focus again on the gray box, you got rid of models, you got rid of costs, you got rid of constraints. And so once you have your parameter policy, the best parameters phi star, then again in real time you have a simple input-output function evaluation. So summarizing, so as you go from MPC to learning MPC to RL and IL, what you see is an increased use of data and a reduced use of design elements. So this is very important because you need to take less and less control classes. You go from the top to down the imitation learning. You have an increased use of learning part. So there is more and more computation happening in the green box, okay? Also, the computation shifts heavily from real-time here. Remember, you need this real-time optimizer to offline design heavy, where you have, even imitation learning, sometimes this training might take hours or days. And the computation heavy also means that it's slower to update your actually real-time policy, right? So if you think about over-there updates here, it's easy to push some new parameters. You will need to push a new neural network. You cannot do that at high frequency. So, and sometimes in some reinforcement learning and imitation learning, you have heavy storage required. So with this background in mind, I'm going to go back to my field of expertise and tell a little bit what techniques I use and what's my experience with these techniques in the application that I'm familiar with. I'm actually remember the 4 class of applications. I'm going to focus only on one, on cars, because cars are, I like cars and they're extremely well understood, and they're they use the it's as I'll show in a second, a very rich class. You have a very rich class of problems within this domain. So these are the cars we've been playing with over the past 30 years. We have passengers cars, which are electric, like Ionic IV, plug-in hybrid vehicles, or internal combustion engine with the Genesis. We also have off-road vehicles for robotic constructions, and small vehicles for like Formula One racing, or a vehicle they've been building 3D printed for off-road inspection. So what's in general, when you think about vehicle dynamics and control, if you just focus on the motion and of the vehicles, you have two classes of models. First of all, you need energy conversion model. This depends on your powertrain and your driveline, whether you have an internal combustion engine, a hybrid, or pure electric. It's about how is the energy how is the energy stored in the battery and the fuel converted in wheel motion. Okay. The second part is how the wheel motion then reflects in the vehicle motion. And here's where you have non-holonomic differential equation describing the kinematic motion of the vehicle with usually an inertial Frenet frame. And then you have dynamics which describe the evolution of variables in the body frame when the vehicle is subject to forces, which are tire forces, as using Newton-Euler equations. The tire force, the interaction between the ground and the tires, is what make the vehicle move. And these are actually the highest source of uncertainty in a vehicle, especially in high performance. And many control methods, many algorithms out there in production use this magic tire formula approximation. So with these elements, okay, now you can build a rich class of problems, and I'll show you next, just focusing on how do I control a single vehicle or a set of vehicles in order to be safe and efficient. The classical one, this is how we all learn feedback control theory, is a cruise control, right? The objective is to use a measured speed of a vehicle to actuate the throttle of a vehicle in order to decide to achieve a reference speed. So you want to minimize the error between a measured speed and a reference speed, and you do that by changing intake air throttle, because this will change the power to the engine, which will change the wheel speed, will change vehicle motion. Now, if you have an electric vehicle, the concept is the same, your actuation will change. So what does cruise control? We all learned this and how to design such a controller. What does a cruise control look like in the era of AI? Well, here is one of the experiments we've been doing that over the past years. This is an automated micro platoons. So you see these 3 vehicles here. They talk to each other. They communicate, and they want to drive through traffic. And they want to do that in order to be energy efficient, so go from A to B with the least amount of energy, and also in order to maximize traffic throughput. You do not want to stop other cars. So what is interesting about this class of problems, that we have well-known models for which vehicle longitudinal motion hybrid powertrain. You have hard constraint requirement, which is the distance between the vehicle of the platoon as well from other cars. You have well-defined cost function. Energy, we want to reduce energy, we want to maximize traffic throughput. And really the data part of here, the AI part, is really means that I'm using data to learn traffic light patterns, when traffic lights switch from green to red and vice versa, and traffic patterns, how much traffic there is in a given road ahead at that time of the day. So this data is then fed into a model predictive control, for achieving this the objective I just mentioned. So here's an experiment. Unfortunately, I'm not able to share the audio with this setup. This is a 3-car South LA. There's a drone. They're talking to each other. They're talking to the traffic light. They know they have a stochastic forecast on when the next traffic lights ahead are changing and what is this traffic ahead. Then the light changes, it communicates the change of phase. And this vehicle, as you can see, the distance between a regular human-driven vehicles, they're promptly going through the traffic light by maximizing throughput. And they do that with a 2-level MPC. The first level plans for speed profile, and the speed profile then it's sent by the leader, and the speed profile is then sent to low-level MPC controller that controls the powertrain and the longitudinal motion in order to be energy efficient. So let me make the problem a bit more complicated. I'll focus on a single car. I'm not going to go at low speeds. I'm going to go at very high speed, and I'm trying to race and trying to design a controller that steers, accelerates, and brakes to that in order to achieve a minimum time on a given path. So again, we have a well-known dynamic models. I teach a class on vehicle dynamics at Berkeley. We spent a whole semester on trying out the difference between dynamic models, which model is better in different scenario. What is really challenging here, what are the tire forces as a function of temperature, as a function of road friction. You have hard constraint requirements. You do not want to really go outside the boundaries of the racetrack. And you have a well-defined cost function, which is minimum time. So here is because of this unknown tire force, we are going now to use a learning MPC. What I'm going to do here, I'm going to repeat, remember the box at the beginning, we had a design part, and I'm going to put in blue what happens in real time. So the learning part, it's a real-time learning. I'm going to take state input pairs in order to estimate the parameters of a safe set and a cost to go function. So I'm using the data to learn as well as the tire model to learn the tire model as well as the feasible set and the cost function. So the idea that we use here in this learning campus is quite simple. We've been presenting this over the years. The target set, as I collected input-output pairs, is actually the convexal of all safe state trajectory that I've recorded in the past. And the cost to go function is the barycentric interpolation of all the cost to go state pairs that I've recorded. So this is if in a one-dimensional space, for a given state, you measure the given cost to go V, and I'm going to take the tightest lower bound, piecewise linear lower bound of this of the data set that I have. This is called the barycentric approach that I've recorded. It's called a barycentric approximation, and I'm going to use the red function as a cost to go. Now, in terms of model updates, what we use here is we linearize the kinematic models, and we use a local in time and space linear regression, which is updated based on the data set that I've obtained. And here now, Newton-Raphson equations are actually used to enforce model-based sparsity. What you see, so summarizing, what's interesting about this theory that I've been developing over the past 7 to 8 years now, is that with these simple ingredients, with the convex hull as a terminal set, with a simple barycentric approximation, you actually have constraint guarantees, and meaning you will never, as you collect data, you will, if you're safe, you will keep being safe. And you have performance improvement, meaning that as the next time you repeat the experiments, you will actually have a cost which is lesser equal than the cost that you measured before. What's beautiful about this theory now is that actually when you run the experiment, this is a passenger car on a racetrack. 100 is the time is a normalized time it takes at the beginning. And you can see after 18 laps, the time it takes to go around the lap is actually decreased of 60%. Okay, so on a full-scale car experiment, you actually see constraint guarantees. You never go out the constraints, and you see performance improvements as the theory tells you. So these are, again, I'm sorry that you won't be able to hear the experiment here, the sound. You will hear the tires squeaking. This is a lap 4 where you almost converge. You see the car opening, now trying to tight and look for the apex, and slowing down and then accelerating when it goes out the curve. These are experiments, and now they go back now to 5 years ago with Ugo and Nitin and Ashwin. So let me move on, and something to more recent we've been doing. I want to use the same setup. I want to have a single car and I want to race it, but I want to do that with camera only fits. The experiment before we used as differential a differential GPS for high precision localization of the vehicle. And I want to do that by actually using only camera. And so what you know here, same characteristic before. We have well-known dynamics, but the challenge is really tire force in these extreme maneuvers. We have hard constraint refinement. I know what is my cost function. I want to minimize time, but now I don't want to use full state feedback. And from what I want to do, I want to try not to avoid the classical approach, which is SLAM and MPC, because that works pretty well. It's still a classical pipeline, observer plus MPC. I want to do that with some form of imitation learning. So I'm going to use a classical trick that is done in imitation learning in a lab equipped with the motion capture system. I'm going to use an expert MPC, which now runs at high speed, okay, where there's full state feedback to control the vehicle. Then I'm going to record as the vehicle is controlled images and inertia measurement. And then I'm going to learn. The imitation learning is done only, okay, on input-output pairs with neglecting the full state feedback. Okay, so this is it's a classical end-to-end control with privileged learning. So now once I have trained this neural network in real time, as I said before, all what I need to do is to evaluate the parameter neural network once I'm given images and inertial measurements from the vehicles. So here, this is an image sequence. It's an image sequence. So what is our experience with this system is that it's been extremely hard to make this work. In fact, this still to today, after a year, doesn't work reliably at very high speed. And so this is a set of what you see here, whether we have a single car or multiple cars, a lot of all failed experiments with our setup. Okay. Now, as you see from the slides, there are my colleagues in other fields. They're seeing impressive performance of these techniques, and for drones racing, for simulators of cars at high speed. This is our experience with this type of techniques, and to date we're still trying to explore how we can improve and why things do not work well in this setup. Let me move now to one of the last example, and it's now go back to low speed, and I'm going to have a set of 4 vehicles now moving in a cluttered environment. So what you have here is a classical multi-vehicle path planning, but what's happening in the environment is very tight. I have vehicle 1 wants to go where vehicle 2 is. That's the green line. Vehicle 2 wants to go out to the left. Vehicle 3 wants to go where vehicle 0 is, and 0 wants to go to the right. So, but 0 is pointing forward, so he has to back up and then go to the right. So this is what's interesting about this. This is a very simple nonlinear kinematic model. You have hard constraint requirement, but these constraints are actually dynamics. As the vehicle moves, then the safe space changes with time. You have also a very well-defined cost function. You want to do that in a reasonable time and end up in a terminal terminal set in a terminal state, which is provided to you. So what's interesting about here that the plain vanilla reinforcement learning MPC do not work here. Do not work here because this is high dimensional space, and an MPC, you will need long horizon to solve this problem. It's a highly non-convex problem. The solver will fail to find a solution. In reinforcement learning, what you're going to do is that you need fine-tuning acceleration and braking and steering. If you try to write down an NDP problem, you will not converge to a solution to this problem. Okay, to a solution that avoids collisions. Okay, so what we do here, okay, is actually a mix of the two. We use a reinforcement learning for a long horizon strategy, and we use MPC with a kinematic model constrained by the strategy that's provided by RL. And the strategy provided by RL it's a classical strategy which is obtained with a checkerboard model. So what you see here, you see a checkerboard. The vehicles are the boxes. Each color, the square box, each color is a vehicle, and the darker versus the lighter, this defines orientation. So darker white means this is the front of the white vehicle. Darker red is the front of the red vehicle. Darker green is the front of the green vehicles. Where do they want to go? Where the circles are. So the darker white, the lighter white wants to reach the lighter circle box, and the darker white, this gray here, wants to reach the gray box, and so on. So we play like in a chess reinforcement learning with the self play here, like on a checkerboard. And the policy, we learn this offline. The policy then, instead of implementing the policy, is fed as a target set to a low-level MPC controller, which uses a kinematic model of the vehicle and which optimizes over continuous space actions of steering, acceleration, and braking. So what you see here is a solution. Okay, the left-hand side is the replay of the RL solution, and what you see here, you see that the RL suggests to bring the white vehicle in this configuration. This is fed, which is vehicle number 2. It's fed to MPC, which brings the vehicle number 2 in this configuration and avoids obstacles with other vehicles. So if you see the full solution, focus on the right-hand side, you see the vehicles nicely solve the problem that was given before, avoiding collision. Okay. Let me conclude. Sorry, this is before I conclude. This is not just a academic exercise. You can actually collect data. You collect data from a parking lot using drones. We use companies to actually tag this data, and this data can actually be fed to improve the performance of the strategy policy. And as I said, this is an actual issue with self-driving cars. You probably have seen this, the videos of Waymo honking at each other downtown San Francisco. And again, the issue is that without replaying the video here, the issue is that it's a tough multi-vehicle problem in tight constraints, which is, as we predicted 5 years ago, is extremely hard to solve. And so, we had 3 theses about this. If you're interested in this class of problems, you go on our website, mpc.berkeley.edu, you will find interesting references and data set to solve this class of problems. So let me conclude with one problem, which is a path planning at complex non-signalized intersections. This is a class of problems where I do not know how to solve this in real time, without a lot of heuristics. So what you see here, you're at the white car, you want to go to the left, you have multimodal predictions of the green cars, multimodal prediction of the pedestrians in front of you, meaning they multimodal in the sense they can accelerate or decelerate on a given path, or they can even change the path. So despite the fact that you have well-known models, your target and cost function are only defined at high level, just cross the intersection, but it's extremely hard to drive safely through this intersection. The the interesting thing is that your behavior will also change the agent behaviors. You have this interactive planning that sometimes researchers solve with some game theory uh, um, um, approach. But the reality is that you really have this combinatorial nature, interactive nature that makes this problem extremely hard to solve. So let me summarize the class of problems you have seen. You have applications where adaptive cruise control with classical mode of adaptive control works. It's, you have AI really means the use of data to update traffic light and traffic light patterns. Here, AI really in learning MPC to race, you really would really want to satisfy constraints. It's unsafe to go off road at high speed. You know, there's you, and you really want to use data to make sure that your performance improves, but you're safe. You have techniques like RL and LL, which are suitable like for this race car example. It's okay to fail. It's okay to crash. It's a small vehicle. You have techniques like our parking with four vehicles where it's the only way to solve this to cleverly merge RL and MPC. And you have class of application that it's today is still hard to solve systematically by any control technique. So one thing that I want to point out here, that's people ask me, so is this AI a revolution or a tool for automatic control design, right? And I think while this gives you my experience with using these tools, this picture doesn't tell the whole story because I think it's very control centric. There is another non-control centric view of AI where it really means the use of AI means a massive use of compute power to run billions of simulations to train your your policy. And this is what you see behind a lot of tuning of cost function for self-driving cars or for walking robots. AI means sensor abundance in all the devices we have out there with cloud contextualization. For instance, I'm trying to understand friction coefficient by using a multitude of sensors on the vehicle as well as weather forecast. It also means the fact that these devices are globally connected and you can have a over-the-air update of control feedback allows you really to design controllers that don't work, deliver them, and actually collect data and improve their performance as people use this type of devices. So let me give you an example, okay, non-automotive related, which will be an example for which I've been involved. This is a solar power plant. What you see here, this is a 300 megawatt utility scale. Each one of these squares is it's a row, it's a trackers, and independently, it's a square. It's a rectangle metal with solar panel that it's independently controlled to track the sun. You have thousands of this, and Nextracker is the leading provider in the world of solar trackers. The optimal angle of of each tracker depends on neighboring tracking angles because you don't want to be shaded, otherwise you lose power. Depends on terrain geometry. It also depends on the amount of diffuse light versus direct light. You do not want to be pointing at the sun in a cloudy day because you want to collect more diffuse light. So what you can do here, you can bring and simulate these massive solar power plants. You can use GPU to simulate direct versus diffuse light. You can also simulate ground reflection because some of these panels are artificial, and individual tracker shape. You can then train your model on an abundance of sensors. We have around 2.5 million sensors on a 300 megawatt plants. And you can use actually the fact that these solar power plants are connected to actually upload new controllers and new controller parameters. So Nextracker, we have built a product on this idea that is called True Capture that delivers by optimally changing the angles of each individual tracker can deliver up to 6% improvement. And really, this has been a game changer in the industry of solar power plants. We started in 2019 where we had 20 gigawatt fleet, and a 6% improvement meant a 1.6 gigawatt. Today, 5 years, 6 years later, okay, we actually, Nextracker did an IPO, is publicly traded in 2024. Nextracker controls 100 gigawatt fleet of solar, and we are shipping the solar field of a size of city of San Francisco every day, okay? So this shows you the power of using data, AI, okay, in the context where feedback control is simple, but the value is really brought by simulation and machine learning. So let me conclude. We have 10 minutes left here on the role of AI in control theory. This is the hardest part of my talk because I've been thinking a lot about this, and be great. Usually I get lots of feedback and questions in this part. It is still an open part of my talk, but happy to share next what I've been, the things I've been doing and thinking. First of all, what is control theory? As I said, I like to define things, and this is a nice definition from Richard Murray that says are principles and methods used to design engineering systems that maintain desirable performance by automatically adapting to changes in the environment. So there's no doubt that we have a massive amount of methods that are AI inspired. Every day there are hundreds of papers and archive on AI and control, new AI and control methods. In terms of principles, this is the hardest part because the question is, do we need new principles? And it's really in looking at my lab today, the principles we use are actually simple and old principles. They're just combined in an interesting way. Okay. So what principle we use? If you think about our learning model predictive control, the first principle we use is dynamic programming. In 1950, it teaches you how you separate a long horizon problem into a cost, a stage cost, and a cost to go. It also teaches you, very importantly, how to compute the cost to go based given a data set. The second part is Taylor's principle that teaches you that local linear models are good in small neighborhoods. And of course, if your data is scarce, you need to increase the neighborhood size, but then you will get a large error. The third part that we use is invariant set theory. And in particular, the 1980 teaches you that if you start from a state that is safe and your predictions land to a safe set, then the whole trajectory, the red trajectory, is also safe. Lastly, we use Lyapunov theory that it tells you that if you use the barycentric approximation, the way we build the terminal cost, this will be a Lyapunov theory, and therefore the energy function will decrease in closed loop. And this is what guarantees really the fact that your performance increases every time you use data to update your system. So let me go and try to tell you why these principles are interesting the way we use it. So what you see here is our little race car, 5 experiments, starting from a lap time of 12 seconds and running, each experiment runs 18 laps. You see the experiments are on top of each other. These experiments are they're easily, you can reproduce them because of the motion capture. You see this kink here. This is because of this is a small vehicle. The actuators are not perfect. What we do here, as I told you, we use this simple way of building a safe set and learn Lyapunov function using barycentric approximation. What happens if we don't do that? So this is a simple study where we have used the same experiments, and I take my state value function pairs and I use a neural network to approximate the cost to go. And then everything else stays the same. This is what happens here. There's a function of the hidden layers of the neural network and the type of neural networks. So it's in red, you have where you violate constraints, the car crashes, and or where actually the performance stops improving, the vehicle actually stops. In green is where the minimum lap time is reached. So it's very hard to predict on how many layers and which type of which type of activation will give you the better performance. I mean, there are today lots of studies on that is a better understanding of guaranteeing safety with this type of networks. I mean, the point here is that there is no need for these applications because simple barycentric approximation work extremely well. Let me do another test. This experiment works really well because we start with a tuning that has a lap time of 12 seconds. So the cost is actually tuned that the initial lap time is low because a slow exploration gives you more data points. You have more data points, gives you better local linear models. All 5 tests are successful. Remember, there are 5 of these curves, one on top of each other. What I've done here, we have changed the tuning of the initial cost so that the beginning you go fast. If beginning you go fast, you are more aggressive, you have less data points, you have bad local linear model, you violate Taylor's principle. And what happens here, these are the lap time as a function of the lap number for 5 tests. 3 tests, okay, are yellow and 2 fail. So this test fail in lap 2 and this test here fails in lap 17, okay? So what's happening here, you're violating Taylor approximation. And from a control point of view, this is well studied. There are well known, if you use classical control theory to address these issues. So this is the part which I'll skip today. I've been, without the audience in front, I go too slow. So for instance, there are many ways to address this, but one way would be to use state inputs pairs to learn and quantify an uncertainty, and then use this quantified uncertainty in a tube MPC setting to robustify the control design. So robustified control design means that instead of nominal constraints, you shrink the constraints by using Pontryagin difference of your state set and your input set with some error tube that you have computed using data. So, and if you do that, okay, here is if you compare a learning MPC with a robust learning MPC, what's beautiful about this theory is that here you expect on the experiments, you see exactly what you expected. This is slow tuning, nominal and robust, they both work well, 5 experiments each. Of course, the nominal is less conservative, so you have the yellow line below the green line, which is the robust. Now, different initial tuning, were more aggressive. The nominal fails twice. The robust actually does not fail in all 5 experiments. So the message here seems to be, well, our lab uses simple old principles. It seems everything works pretty well. Is there new space for new principles? So could I write that principle on learning rate in learning MPC? I think yes. The problem is, and I would really recommend you to look at this talk from David Donahoe, which is really focusing on the shift from theory improvement to empirical evidence in every field. And so I took one of his slides and I made it mine, in the sense that I took something that I was doing 25 years ago, writing theorem of robust MPC, and the majority versus now, the majority of the papers that we write are mostly tables on these complex raising vehicles experiments. Not mostly, but more than half of our papers end up with tables, because it's hard actually to build principles around this type of control design. And so what is the issues with this? The issue is that table needs a benchmark, and our community does not have benchmark. Each experiment is different. Even if we use the same Formula One race experiment, each one is a different build of that Formula One race. There are different friction coefficient, and our community is not great at doing benchmark. the principles actually need a community focused on similar design, and because we are fragmented, if you go back to the first slide of this talk, it will be not be really useful to build a new principle for a very fragmented community. It's also from some learning pipelines like end-to-end is not realistic to expect a new principle. So however, okay, I showed you that there is value in using principle design. For instance, especially when you need hard constraint satisfaction, when you need to maintain these controllers, and when you need to update and update a policy that changes a control design all around the world. I think the other message of today, and I'll conclude with this, is that I think there's really a need of principal control design in learning control architecture. What I mean by that is that, as I showed you, I gave you two types of architecture, more of a model-based optimization versus on the left-hand side, and more of a, on the right-hand side, a learning RL imitation learning architectures. The reality that in practice, they really look like more complex than this. The classical pipelines are hierarchical and multi-layered. This would be a pipeline in a self-driving vehicle where you have a mission planner, a global planner, a local plan, some low-level control with a mix of state observer and feedback control. Even classical IL and RL pipelines actually have network divided into architectures. Okay, and so the reality is that I do not believe there's really the reality that there's really no principled way to design these architectures today. I will conclude. I will skip many of the slides that I have here. Okay, and I'll conclude. I'll go directly to my final slides, where I told you today a fragmentation. I discussed the fragmentation of our field. I tried to give you some my thoughts on the role of AI in control theory and the role of AI in control application. So from what regards the fragmentation of our fields, I talked about the burden of knowledge. There's really not much around this. We need to just absorb more and able to discern facts from fiction. It's extremely hard for young students, but I do not see really much room around this. And in my own talk, for instance, today I told you this talk was pretentious. For instance, I skipped a whole big class of AI and control based on large language models for control. So, and there are two, I'll share the slides with you. There are two interesting papers on how to use large language models for control engineering, as well as how to use large language models. So this would be designing classical control actually to close the loop with large language models. For regarding AI and control theory, I talked about the tension between theory improving and empirical evidence. Very hard to assess really what really works. We need common benchmark. I also show you the value of using principle design in control process, especially when hard constraints are important. I also told you that I think the future is really trying to understand principle design of learning control architectures. Finally, okay, the role of AI in control applications. I think it's clear there are divergent opinions. I hope that I gave you the impression that I don't think it's so black and white. There is really room to merge both worlds to push the boundary of what can be controlled today. And I think most importantly, as long as you have a beautiful, a good problem motivation, okay, this is really what you should be looking at, a good cluster problem and motivation. Then you'll need to merge both worlds in the days ahead. I think this concludes my talk. Thank you for your attention. It's 10 o'clock. I'll be happy to take a few questions.
Thank you so much, Dr. Borrelli. We have a couple of questions, and the first question is from Viet An, and it's a bit.
One second. Sorry, for some reason the volume.
Oh, sorry.
Go ahead.
Yeah, can you hear me?
Yes.
Yeah. So The first question is from Vietnam. I've posted it in the chat because it's a long question, but I will read it out just for the audience. So, uh, are you able to see the question?
Yes.
Yes. Just to read it out, related to
Yeah, no, I
NPC.
can see that. That's a very, very good question. I in it, first of all, if there is the question is if there are the approach consider dependency between decision variable DRL and MPC layer. The answer is no. In that simple approach, the answer is not. And in fact, you're right. You do not have guarantees. That approach doesn't provide any guarantees, right? So would be interesting actually to think of how you couple decisions at different abstraction levels so that you can provide guarantees. There are a few techniques out there. We also have published some papers. However, it's extremely hard. They are overly conservative. Okay, and so what I showed you does not have any guarantees, and there is no coupling between the decision between the two layers. Very good question.
Yep, thank you. And the next question is from Andreas our Professor Malakopoulos. So it's I've again pasted it on the chat. So it's about your thoughts on LMPC to optimize the powertrain of a car with respect to
Driving
driving
style.
style.
No, that's an excellent question, and Andreas. And um, it is can be done. I think it should be done. Maybe we should write a project together. I think the challenge, as you know, it's really to be within the regulation, regulatory constraint, right? But I think it's a very good point. If you can collect data and you can make sure that the powertrain performance is optimized for your own driver style. So I think it's a very good point. We haven't done that. We have done that at the vehicle dynamics level, not at the powertrain level. I think as long as you can enforce regulatory constraints, that is a good point, and we should be doing that.
So thank you. And this is more of a question from personal curiosity. So when we have like human drivers involved in these scenarios, how maybe this is about hard constraint, or like how should one approach when like it's in a mixed traffic scenario per se, uh, in these sort of applications.
You're asking how should we approach when we have, in terms of predictions as a driver, in terms of control of a car where it's not an L4 car, but there is also a human driver.
So it's more like it's more on at the control level, but maybe it's so whenever there is like an autonomous vehicle and a human-driven vehicle interacting with each other, so there is this aspect of predicting what the human would do next, and also reacting to that predictions and considering all of these
So
things.
yeah, so this is the last part, right? It's just I
Yeah.
don't know how to do that. I mean, clearly there are hundreds of papers on that, and each one has a different interesting angle. Today, you have a variety of driver models, and if you are a company that has these driver cars out there, you have a huge amount of data to fit these models. Okay, so your motion models are decent today. Your motion prediction models, of course they're uncertain, and the question is how do you handle this uncertainty, multimodality, and interaction at the same time, right? I do not know how to do this. I know, clearly the classical, a formal way would be you could set it up as a game theory, but the reality is that is not how we drive, okay? And this is, and also it's not real time feasible. And so that's why I mentioned there's a lot of interesting heuristics today used to solve this problem. There's a classical nudging forward. And that actually cars do today in San Francisco. But I do not believe we have a systematic way of doing that in real time. Okay, that is real time capable.
Thank you
Thank
so
you
much.
for inviting me today.
Yeah,
It's a pleasure to talk to you all.
yeah, it was a pleasure having you.
Thank you. Bye
Thank you
bye.
so
Bye.
much. Bye bye. Bye bye.